Hello, in today's video we're going to be looking at chapter 11 and working out some problems for it. So first thing we're going to look at is at the very beginning of chapter 11 when we were talking about the kinetic energy and intermolecular attractions that were in our different types of substances or different physical states. So within our different physical states, we're going to have different amounts of kinetic energy versus intermolecular attraction. So kinetic energy, more things moving around. Intermolecular attractions, greater intermolecular attraction, generally is going to result in things not moving quite as much, being stuck together. So if we have a solid, then we have a substance that is going to want to be close to everything else, right? Nothing moving very much. So we're going to have very low kinetic energy, and since everything's going to be very close together, we're going to have high intermolecular attractions. So we're going to have a state where you have a kinetic energy much less than intermolecular attractions between particles. Okay. Next, we want to look at our different intermolecular forces. We want to rank them from high to low. So highest energy versus lowest energy. So our intermolecular forces, we talked about ones in pure substances and mixtures. So we're going to look at all of those. So our intermolecular forces from strongest to weakest. Our very strongest is ion dipole. And this only exists in mixtures. After that, we have hydrogen bonding. This can be in mixtures or pure substances. Next, we have dipole-dipole. Also pure substances or mixtures. After that, we have ion-induced dipole. Ion-induced dipole. And this is only in mixtures. And lastly, next to dipole, induced dipole. Also only in mixtures. And lastly, in weakest, induced. So energetically, we are going to go like this. So energy-wise, our ion dipole is going to be the strongest. Our induced dipole is going to be the weakest. But keep in mind that our induced dipole is going to be affected by molecular weight. So we can get a fairly significant induced dipole just by making a larger molecule. Okay. Now let's look at our dominant intermolecular forces in the following pure substances or mixtures. So what are the dominant intermolecular forces? There are, of course, every substance is going to exhibit induced dipole, but I'm looking specifically for the dominant intermolecular force. Pay attention to what I'm asking with these, because sometimes I'll ask you for all of them, sometimes the dominant. Here, I just looking for dominant. Okay, so the first one, N2. Looks like this. So this is a nonpolar substance. And as such, the only option we have here is induced dipole. Between our N2 molecules. Okay. Next, we have water. And so next we have a mixture. We have water. Looks like this. And then we have formaldehyde, which looks like this. Okay. The left one can hydrogen bond with itself or with others. The right one is dipole with itself. But if we mix it in with something that has the ability to hydrogen bond, since it has an electron pair, it can also hydrogen bond. So this would be hydrogen bond, or hydrogen bonding as the dominant intermolecular force here. Next we have a pure substance, heptane. So this is going to be a long hydrocarbon chain. Looks like this. Each of the points is a carbon, and it'll be surrounded by hydrogens. The only option we have here, since this is non-polar, is induced dipole, induced dipole. Okay. Next, we have water and sodium chloride. Water, we already looked at, but it looks like this. Has the ability to hydrogen bond. Sodium chloride looks like this. All right, so we have ions. Put them together, we have ion dipole. Okay. And now we have N2 and H2O. N2 we've already looked at, but looks like this. It's a nonpolar substance. H2O looks like this. So our option here is dipole, induced dipole. Okay. So now we want to rank the strengths of the intermolecular forces relative to each other. The strongest here is this one, our dipole or ion dipole. It's going to be our strongest one. Next would be our water formaldehyde with our hydrogen bonding. And then we have some nonpolar London dispersion forces as the last three. Dipole, induced dipole is going to be the strongest of those, although still not that strong of an interaction, and there's not going to be a very large amount of N2 that's going to dissolve in water because we have to break hydrogen bonds in order to get this dipole-induced dipole interaction to occur. We do know, hopefully, that some gases will dissolve in water because they're both small molecules, but not a very, very large degree. Okay, next we have 2 induced dipole. Remember, induced dipole is going to be based on molecular weight. So our next strongest will be this one because heptane is a lot larger than nitrogen, which will be our weakest. Moving on, we've got the following table. I want to fill this out. I guess I'm doing it myself, sorry. I want to fill this out with the intermolecular forces that exist, relative viscosity, and relative surface tension based on their structures and the following properties. So first we look at water. We know all of our things can do induced dipole, right? So all of these, no matter what they are, will exhibit induced dipole or London dispersion forces. Now we look at our substance. This is a polar substance. This is non-polar. This substance has regions of polar and non-polar. Okay? So the polar substances will do dipole, dipole, okay, and then this has a oxygen-hydrogen bond, so it can also do hydrogen bonding. Okay, now viscosity is based on intermolecular forces, but more importantly, it's based on length of our substance. So the longer, more electrons, more tangling that can occur, the greater the viscosity. Then we look at intermolecular forces after that. So intermolecular forces, if we have a long tangleable substance, will result in a material that has a high viscosity. So the highest viscosity is going to be this one because it has those long carbon chains. So we're going to call this 1. Next we have water and methane. Both of them are close in intermolecular or molecular weight, so weight is not going to have an effect. The only thing that will have effect is our intermolecular forces. So this will be next. So we'll go out the middle for 2, and then this is going to be the lowest Okay, surface tension is almost completely dominated by intermolecular forces. Greater intermolecular forces will result in greater surface tension. So our water has the greatest intermolecular forces, so it's going to have the greatest or highest surface tension. Now, our fat over here, the one with the polar and nonpolar regions, is going to have the middle, and then our lowest again will be methane because it has very, very weak induced dipole interactions. Okay, let's try another one. So we have the following diagram, and we want to look at our different changes in state. So going from a solid to a liquid, then a liquid to a gas, and what's going on. So if we want to go from a solid to a liquid, that is going to be a endothermic process. It's going to require energy, like so. And we call that melting or fusion. Okay. And then going from a liquid to a gas also requires energy. We call this vaporization. And then going from a solid to a gas, or less endothermic process, this is sublimation. Okay, let's go the other way. So let's look at our exothermic processes. Going from a gas to a liquid, called condensation. Going from a liquid to a solid, freezing. And then going from a gas to a solid is called deposition. Next one, we're going to start to finally actually get some calculations in here. Is asking to calculate the heat required to heat 25 grams of ice from negative 10 degrees Celsius to 125 degrees Celsius. So we're going to be looking at, since we're going through temperature changes, we're looking at our specific heat equation. When we're looking at phase changes, we're looking at a more simplified specific heat equation. So we have a temp change within the same phase. We use Q. The energy of that is equal to mass times by our specific heat times by our delta T. Remembering our specific heat is phase dependent. And then our phase change is Q is equal to moles times by our enthalpy change. So we've got all the information we need here. We need to first, since we are going to use moles, convert from 25 grams into moles. So we take our 25 divided by 18.01. And that gives us 1.39 moles of H2O. Okay. Now we're going to go from our lowest temperature up to our melting point. From our melting point, we will melt. And then from that point, we'll go up to our boiling point, boil, then go up to 125. So our first temperature change is going from negative 10 degrees Celsius to 0 degrees Celsius up to that melting point. So our Q here would be equal to our mass, 25.0 grams, times by our specific heat of ice, because we are in this solid phase. So 2.09 joules over grams times by degrees Celsius, and multiplied by our temperature change, which is 0 minus 10, which is 10.0 degrees Celsius total. Multiply all that together, we get a energy of 522.5 joules. And I'm going to convert that into kilojoules, 0.523 kilojoules. Okay, next we want to melt. So our Q will be equal to our moles, 1.39 moles, times by our heat of fusion, 6.01 kilojoules over moles. And multiply that out, we get a value of 8.35 kilojoules. Okay. Next, we're going to go from 0.0 degrees Celsius to 100 degrees Celsius. So we've melted. Now we're going between all of our temperature ranges of water. So Q is going to be equal to 25.0 grams times by our specific heat of water, 4.18, times by our temperature change, which will be 100 degrees. Which gives us 10,450 joules. Again, I'm going to convert into kilojoules. 10.5 kilojoules. Then we need to evaporate. I'm actually going to put evaporation over here. Room. So this is going to be Q is equal to our moles, 1.39 moles, times by our heat of vaporization, 40.7 kilojoules per mole. Solve that out. We get a value of 56.6 kilojoules. And lastly, we're going to go from 100.0 degrees Celsius to 125. So we take our 25 grams times by our specific heat of steam, 1.84 joules over grams times degrees Celsius. Calculating that out, we get a value of 46.0 joules, which will be equal to 0.05 or 46 kilojoules. And then we are just going to sum all of these values together. Q total is equal to 0.523 kilojoules plus 8.35 kilojoules plus 10.5 kilojoules plus 56.6 kilojoules plus 0.046 kilojoules, giving us a total of 70.0 or 76.0 kilojoules. Okay. Okay. We're going to freeze water at 0 degrees Celsius, and we want to know which of the following statements are true about the equation below. H2O liquid to H2O solid. Both the forward and reverse processes have stopped, so there is a set amount of solid and liquid at 0 degrees. Only the forward process has stopped, going from liquid to solid. Only the reverse process has stopped, going from solid to liquid. Both the forward and reverse processes are proceeding. They're just occurring at different rates. Or both the forward and reverse processes are proceeding at the same rate. Hopefully, you realize this means that we are in equilibrium because we are at the freezing point or melting point of water. If we were above or below, we would not be at equilibrium, but we are at equilibrium. Therefore, this will be our true statement. Okay. Next, we want to look at which of the following will affect the boiling point of a substance. Molecular mass of the material, intermolecular forces, the external pressure on the material, or all of these. Okay, so we know boiling point is when vapor pressure is equal to atmospheric pressure, and we know that as we have greater things holding substances together, the harder it is to pull it apart, so the harder it is to achieve boiling, right? You have to break all of the particles apart in order to go from a liquid to a gas state. So all of these are going to be important. The external pressure will affect vapor pressure, and then the other two will affect how tightly the substances are held together. The substance is held together. So all of this will affect our boiling point. Okay. Let's try another example where we have a little bit of math going on. So now we're looking at enthalpy of vaporization using vapor pressure. Hopefully when you see that, you know Clausius Clapeyron. Okay, so we need to look at the things that we have and determine, this is what we know we need. And in the equation itself, it'll tell us, or the word problem above, it'll tell us what we actually have. So our normal boiling point is 61.7 degrees Celsius. Enthalpy of vaporization, 31.4 kilojoules per mole. And we want to know what our vapor pressure is at 25 degrees Celsius. So this is going to be T1 right here. This is going to be T2. This is going to be our delta H. And since we have a normal boiling point, that means that P1 is 1 atmosphere. Okay, so we're solving for P2 in this case, and we have everything else. So ln 1 atm divided by P2 is equal to negative 31400 joules per mole. Okay, I have converted my enthalpy of vaporization into joules per mole. Okay, make sure you pay attention to that because our R value is in joules per mole Kelvin. And we need our units to cancel out. And since we have Kelvin, our temperatures also have to be in Kelvin. So 61.7 plus 273.2 gives us a value of 334.9. So our T1, we 1 over 334.9 Kelvin. Okay. I'm going to subtract that from our T2, 25 degrees Celsius, also equal to 298.2. we solve for this, solve for the right side, we get ln 1 ATM over P2 is equal to 1.39. We take the ln of, or the e to both sides. We get 1 ATM over P2 is equal to 4.01. And if we solve for P2, we get a P2 equal to 0.250 ATM. So we have a decreased temperature, so we should expect a decreased P2. And that's what we got. Fantastic. Okay, last question here. We want to fill in the following phase diagram for CO2 with the terms listed. Solid, liquid, gas, triple point, critical point, and supercritical fluid. Okay. So first, our solid is going to be the most condensed phase of matter. So it's going to be this one over here. And then our gas is going to be the least condensed phase of matter at the highest temperature. So this one right here. Okay. And then our liquid's going to be in between. Okay. Our triple point is where all three phases exist, so right there. And our critical point is when we have our liquid and our gas kind of at the same density. And after which, that point, we no longer have a differentiation between liquid and gas. So there's our critical point. And our supercritical fluid is right here. So after our critical point, why did I just put liquid there? I didn't do that. That's supposed to be supercritical point, or critical point. After our critical point, we have a supercritical fluid. Okay. That is everything.